Welcome to the next lesson in the Earth and Space topic. Today we are looking at the magnetic Earth. Usual procedure at the start, folks. There are 4 images there, and again, starter activity containing 2 questions. I'd like you to pause the video and spend a couple of minutes thinking about it. I'm sure you know quite a bit about magnetism already, so what can you recall before I go through anything? I'll give you a countdown, and I will be sharing my thoughts in 3, 2, and 1. We'll look at question number 1 first of all. Compare and contrast. Now that's quite a popular question that they like asking students in tests, and you've got to be clear on what it means. Compare, what's similar, contrast, what is different. So let's compare gravity and magnetism to start off with. What have they got in common? Well, they're both forces that can affect other objects. Okay, you got that so far? Now, in terms of the kind of force they are, we'd call them non-contact because they can affect other objects at a distance. So that's things that they've got in common. They're both non-contact forces. Contrast, there is quite a bit of a difference between the two. If you think about it, from last lesson, gravity can only attract pulling things towards it, downwards if you like. So that's an attraction. Whereas magnetism, I'm hoping you're clear on this one already, magnets can both attract and repel. So that's a difference as well. What kind of things can gravity attract? Is there any limit of anything? You pick anything up and let go. Is there anything you can think of that won't be pulled down? Have a think. Bet there isn't, because gravity will attract anything. But what about magnets? What can they attract? Again, we're looking at that this lesson. What do you know already? What do those images tell you about magnetism? Question number 2. Well, there's a whole host of things there. I'm not going to go into it in detail now because we're covering that in the lesson. So what's the work in progress today, sir? I can hear you all asking. So let's have a look at the objectives. First of all, very quickly, we're going to look at which metals can be magnetized. Again, then we're going to look at the shape of a magnetic field, the direction of it, and we're going to think about how different poles affect each other. We're going to describe the shape of a field between 2 magnets in different kinds of arrangements. Again, that's to do with why like poles will repel and opposite poles attract. I'm sure you know that already. And then finally, we're going to compare the Earth's magnetic field to the bar magnet we've been looking at earlier in the lesson. And again, we're going to link that to how compasses are used for navigation. So that's the work in progress today, folks. Get your sleeves rolled up. You will need a paper and a pen. I'm going to strongly suggest you make notes as you go through this, just like you would in a classroom. Right then, into that first objective. Which metals are magnetic materials? Which will be attracted to a magnet? There are a lot of metals out there, but there's only 3 which are magnetic materials. There's a few metals there. In there, 3 of them are metals that can be made into magnets or be attracted to another magnet. Do you know which they are? Have a look through. I'll click the answers up in 3, 2, and 1. So we've got symbols there for several metallic elements. We've got gold, magnesium, iron, copper, nickel, silver, aluminium, cobalt, and zinc. And out of those 3, iron, nickel, and cobalt, can be magnetized, or are, as we would say, magnetic metals. Just those 3. Make sure you made a note on that. You need to know it. So, as that says, how familiar are you with the periodic table? Can you find the 3 magnetic metals? Off you go. I'm going to click up the answers very shortly. Once you've found one, it should be dead easy to find the others because they are all together on the periodic table. And again, it's no coincidence as to the fact that they are together on the periodic table, and those 3 are the only ones that can be magnetized. We're going to look at that in a little bit more detail. So, how does iron become magnetized then? The little FYI in the corner there is to tell you that this is just for your information. It's not something that we're going to test your understanding of in any exam coming soon, but hopefully it's interesting. So there we've got a diagram that represents unmagnetized iron. Okay, and again, magnetism is a property of the atoms of those magnetic materials. And we talk about little groups of atoms as what we call domains. And again, we can see from that first diagram, all of those domains are jumbled up. And because they're all jumbled up in different directions, they cancel each other out. So therefore, your ordinary piece of iron is just unmagnetized. Now, if we line the domains up, there we can see partly magnetized iron. And if we align them even more, we end up with strongly magnetized iron. So when a magnetic material has become magnetized, the domains, these groups of atoms, they've all been lined up in exactly the same direction. I'm going to show you how that's done a little bit later on. So again, that's just for your information, but hopefully find it interesting. Certainly helps you to understand magnetism in a bit more detail. I love this clip. It shows you just how strong magnets can be made if you line up all of those domains. Wow, look at that. It even gets that sledgehammer right at the end. Here it comes, and it doesn't fall off the table. You've seen these before. What I'd like you to do is fill in the missing words. Nice little animation or clip there that's showing iron filings being sprinkled around a bar magnet. If we were in school at this moment in time, you'd be doing that with us in the classroom to see it for yourself. But that clip, I think, it shows it quite nicely, actually, so you should get the same idea. So anyway, I'd like you to fill in those missing words. I'll click up the answers in 3, 2, and 1. So the region around a magnet where it has a magnetic effect is a magnetic field. When a magnetic material is placed in a magnetic field, it will experience a force. Remember, we mentioned that at the start. Again, what kind of force is it? It's a non-contact force. If you think about it, magnets will attract towards each other at a distance. You bring them close together and they'll do that last bit of movement themselves because it is a non-contact force. So the iron filings feel the effect of the magnetic field and show the direction of the forces around the magnet. You're not sure what iron filings are? Imagine getting a really, really strong cheese grater that's strong enough to grind up iron, and you'd end up with little flakes of iron. And obviously iron is magnetic material, and they line up very nicely. We actually call them induced magnets, those little pieces of iron, but I'll let you worry more about that one in GCSE. So what is the shape of a magnetic field? What are the directions of the lines of force in that field around a bar magnet? I'm going to show you an image here. I'm sure you've seen it before. So initially that showed some iron filings, and what we've done there is drawn the field lines over the shape that the iron filings has showed us. 2 questions. I would like you to freeze it at this point, think about those 2 questions, and then answer them in your notes. So off you go. Answers coming up in 3, 2, and 1. So which way do the lines flow? If you look at that, the arrows clearly show that the field lines are flowing from north to south. Again, you do need to know that. Where is the field strongest? It's strongest at the poles. And we can clearly see that because the field lines are much closer together. And converse to that, it's weakest at the furthest point from the poles, in the middle of the equator, if you like, between those 2 poles. The lines are further apart because the field is weaker. You can see the same effect. More iron filings have been attracted to the poles because it's stronger, a stronger magnetic field at those 2 poles. So, plotting magnetic fields. As we've seen, iron filings are useful, but it'd be hard to draw the magnetic field by drawing around the iron filings. So, using a compass gives us a much clearer picture. So, we'll look at how that's done over the next slides. So, using a compass to show the magnetic field step by step. So initially, you place your bar magnet on a piece of plain paper and you place your compass next to one of the poles. Use the south here, it wouldn't really matter. And you then place a dot by the red needle. You then move the compass away and you place the white needle over the dot you've just drawn. And again, you place a dot by the red needle. Same process, move the compass along, place a dot by the red needle, and if you carry that process on, you'll end up with a diagram that looks like that. By repeating that process further out and further in, you can show the pattern of the field lines as you move away from the magnet. There will come a point eventually where the magnet is not close enough to the compass, you've moved the compass too far away, and it won't be affected anymore by that magnetic field. Repeat the process in diagram 6 for the other side of the magnet, and what you'll end up with is a diagram we'll see shortly that shows those field lines on both sides of the magnet. Just including that image there, it shows very nicely how the compass needle is affected at those different points by the magnetic field as it's moved around the magnet. So just have a quick look at that one before we move on. Right, it's one of them bits for you to fill in the missing words again, covering the key points. So what can you remember? Now, if you're dead clear on it and you think you're ready to launch in, freeze the video now and put in the missing words. If you're not sure, I'm going to click up the missing words now. And then I'd like you to freeze the video when I give the countdown, and I'll put the answers up in 3, 2, and 1. So when two like poles are put together, they will repel. When two unlike poles put together, they will attract. Scattering iron filings around a bar magnet makes it possible to see the lines of force of that magnetic field, and a plotting compass could also be used to show the field lines around a magnet, and the compass needle points to the north following those magnetic field lines. Check your answers on that and we'll move on. Have a go at this one then. You should hopefully, from the previous slides that we've looked at, be familiar with the shape of the magnetic field around one bar magnet on its own, with those field lines going from north to south. What would the field lines look like between the poles in those two questions, question 1 and question 2? So I'd like you, again, at this point, freeze it and draw the field lines between the two poles. So again, I'm stressing here, I don't want the field lines around each individual magnet. What would the field lines look like between the two poles in diagram 1 and diagram 2? So we've got diagram 1 showing two like poles, and again, be clear that they are repelling, and diagram 2, two opposite poles, which would be attracting. So freeze it, have a go, I'll show you the answers in 3, 2, and 1. I'm going to click on, first of all, for the first one, a nice little image there that shows what the field lines would look like as shown by iron filings. Now again, because those are two like poles, the field lines will repel. Iron filings actually show that quite nicely, don't they? In that sort of mid-zone, they are repelling away from each other. And we can see that clearly from the diagram I've just clicked up there. And again, it shows those field lines flowing out from the North Pole, and they are opposing each other in the middle. Same for diagram number 2. We've got there iron filings showing us that alignment of those iron filings, of the magnetic field, sorry. And again, the diagram there shows how those field lines are attracting each other. So again, just make sure you made a note on that before you move on. Okay, you're doing great, folks. You've done 2/3 of the hard work. Let's just pause a bit and have fun with magnetic fields. What you can see there, two very strong magnets, and in that jar we have a substance called magnetic putty. and it's obviously affected by the magnetic field between those two magnets. Shows the field lines quite nicely, I think. Magnetic putty, by the way, is kind of like a gel or a jelly, and of course there are lots of pieces of iron in there which are affected by the magnetic field. Another very similar idea in this one. Again, we've got the tube, which is obviously the magnet, and again the magnet is drawing the magnetic putty around it. Rather nice, actually. You can see that magnetic putty being drawn in the field lines as that tube disappears inside the putty. Similar idea in this one. Where's the magnet in this clip then? Oh, come on, stick with us, mate. It's only science. It's not that bad, really. I would love to have enough magnetic drafts pieces to recreate this one. Looks like it's going to take ages, that. And again, all happens rather quickly. Shows rather nicely the same thing as the previous in slow motion. It's great when you look at this one, you can see those opposing poles being attracted towards each other. This one's brilliant, I think. I'll let you have a look at that and ponder what's going on in terms of magnetic forces. Looks like it took a while to set up. As it says, this is definitely my favourite. Hope nobody's got hot dogs planned for tea. Want to put you off your food or anything. Okay, we're into that final objective here, folks. Again, there are 5 questions. Well, 6 really. There's another one underneath. I'd like you to freeze the video at this point and have a think about each of those questions. Some you should be clear on, some you might not, but think about them first anyway before you move on, and I'll talk you through the answers to them. So freeze it and we'll move on. So for the first couple of questions, that compare and contrast again, what's similar, what's different between the Earth's and a bar magnet's magnetic field? Where are they strongest? Where are they weakest? We'll deal with them together. So compare, well, they both clearly have a very similar shape. In both cases, the magnetic field is strongest at the poles and it's weakest in the middle or at the equator, as clearly shown by how close together those field lines are. Contrast, what's different? Notice that for the bar magnet, as we should be clear, we've made a note on that, the field lines flow from north to south. It's the opposite for the Earth. I'm not going to go into that in detail at this stage for you. Clear that one up later for you if you want to know, well, when you need to know more about it in year 10 and 11, especially if you do triple science. So question number 3, how does the magnetic field of the Earth help people to navigate? I'm sure you're aware of compasses, and again, a compass has a very small magnet suspended in the middle, the needle, and again, it points towards the north. Very useful map reading. So they can be used to help people find their way or navigate in the countryside, in the wilderness, because that compass needle always points to the north. Looks like Darth Vader needs to work out how to read a map. Keeps getting lost every time he goes to Disney World. Good job he's got them stormtroopers there to help him out. Okay, so as it says, a bit of home science. Try this one out for yourself. How can you make a compass at home? That's what you're going to need. And this is what you need to do. Now, this method, certainly the first part, magnetize the needle with a magnet, this links to that little bit of extra information I gave you at the start in terms of aligning those domains inside the piece of iron, which is what the needle is mostly made of. So every time the magnet is stroked across the needle, it aligns the domains more. The more you do that process, the more aligned they will be, the stronger you'll magnetize that needle. Notice how it's lifted up every time. You've got to do that. Don't rub it backwards and forwards. That will not work. Then, as it says, place the needle on a float and suspend on water. Little image here to show you how it's done. They're using a cork in this case. Careful sticking a needle through cork. I'm going to suggest you doing things like a vice for that. It could be quite dangerous. Talking of dangerous, try it for yourself, obviously, but please be very careful if you're using those strong, small magnets. There's been quite a few instances of accidents with them, especially if you get them inside you. It can be very dangerous. So check with adults at home first, and whatever you do, keep them away from smaller brothers and sisters. As I said, they can be very dangerous, but if you take care, there's nothing wrong with you trying this one. It does work. I'm sure quite a lot of you had an idea about this one already. What is it that causes the Earth to have a magnetic field? Well, it links to the fact that the Earth has got a core of iron. The outer core is molten iron. The inner core is a solid iron. But that core of iron, which, as you know, is a magnetic material, is what ultimately causes the Earth's magnetic field. So what's the Earth's magnetic field ever done for me, sir? I can hear you ask. Well, you need to be really thankful that the Earth has got one. It's that magnetosphere, as we call it, that protects us from all kinds of harmful radiation that the sun is constantly giving out into the solar system. So it's a good job it's there. We'll link this to Mars. We've thought about Mars before. There is no magnetic field on Mars. So if anybody does go, they're going to have enough protective equipment to be able to withstand that extra dose of harmful radiation that they will get from the sun. As I'm sure you are aware, magnetism is an invisible force. You can't see it, but if you could, that's a little bit like what the Earth's magnetic field would look like. Of course, it wouldn't be coloured. It's just there to show the North and South Pole. Now, in terms of the movement there, that's real. The Earth's magnetic field is constantly fluctuating. And again, that's due to the fluctuations in that molten iron core in the middle of the Earth. Sometimes, interestingly, the Earth's magnetic field changes, literally flips over, and alters in terms of the strength of the field also. We're going to finish off on this, folks. We can't think about the Earth and its magnetic field without contemplating one of the most stunning natural wonders that happens as a result. I bet most of you have an idea what that image is showing. It's showing aurora, or what we might call the northern lights. You might not know this, but there are also southern lights, the aurora australis. And again, as it says there, it's got to be one of the most beautiful natural displays going. Now, they're produced, we know quite a lot about how they're produced, by interactions of the Earth's magnetic field, the magnetosphere, with charged particles that are constantly, if you like, spewing out from the sun across the solar system. And when those particles get into the upper atmosphere, they lose a bit of their energy. Now, as they lose that energy, now don't worry about those terms there. You'll understand them come year 10 and 11, though, I promise. Okay, they cause ionization and excitation of the gases in the upper atmosphere, things like nitrogen and oxygen. The different gases cause the different colours. And again, absolutely fantastic. Never seen them myself, but it's certainly on the top, or certainly close to the top of my all-time to-do list. Just wanted to share a couple of images of the aurora, northern lights in this case. Another one there. Yeah, it's definitely mesmerizing, that, folks, isn't it? Without a doubt. Awesome. This is the privileged view of the northern lights that you would get if you were on the International Space Station. Pretty amazing sight, that one, I think. Not just the Earth that's got a aurora at the poles. Jupiter has one as well. We think that's to do more with a core of hydrogen and helium. Again, not an iron core for Jupiter, but certainly it does produce a magnetic field, and as a result, they have these aurora. A little superimposed image over that, showing the movements of the aurora as the magnetic field fluctuates. Rather nice image there. Very similar thing for Saturn. Northern lights there we can see, and coming around at the bottom, you can just about see the southern lights there of Saturn. I'm going to leave you with this one. What do those animals have in common? Just have a bit of a think. It's got to be something to do with the lesson. What do they have in common? I'm sure you're aware of this idea. Some animals migrate, and again, their ability to do that is to do with the fact that they can detect the Earth's magnetic field. And evidence that they can do this, as it says there, is very conclusive. We know that some animals have that ability. However, how they do it, which organs they use to do it, is not fully understood. I know a little bit about it, not a lot. Maybe there's some of you out there that want to do that extra research. Can you let me know? Find out, because as I said, I'm not totally clear. It's one of them. If you do, get it to me at school, and I'll find a way of rewarding you greatly if you can help me clear that one up. Anyway, we've made it to the end of the lesson, folks. It's been a pleasure. I've enjoyed doing it. Hopefully you've got out of this what you need to. So I will say goodbye. Signing out, Mr. Firth.